Hello everyone. So this is a question from JEE Mains 2026 8th April Shift 2. The incorrect statement from the following with respect to carbohydrates is okay. A, all monosaccharides are reducing sugars. Okay. B, the monosaccharide units obtained from hydrolysis of oligosaccharides are always the same. Okay. C, starch and cellulose are typical examples of polysaccharides which are very high molecular weight compounds of more than 10 monosaccharide units. D. Open chain and cyclic structures coexist at equilibrium that are responsible for certain properties, as in the case of D plus glucose. So the chapters involved is biomolecules. Okay, so let's talk about these statements one by one. So A talks about monosaccharides. Monosaccharides are the simplest carbohydrates which cannot be hydrolyzed to smaller molecules. Okay, and all those carbohydrates which contain aldehydic or ketonic group in the hemiacetal or hemiketal form and reduce tolerance reagent or Fehling solution are called reducing carbohydrates. Very important. Okay, all those carbohydrates which contain aldehydic, that is the CHO group, or ketonic group, which is the C double bond O group in the hemiacetal or hemiketal form and reduce Tollens and Fehlling's solution. So they are known as reducing carbohydrates or sugars. Okay, so when I say that the aldehyde, that is the CHO, or the ketonic group C double bond O, they are in the hemiacetal or hemiketal form. By hemiacetal, I mean in the cyclic structure of carbohydrates, the CHO group combines with an OH, that is an alcohol group, to form hemiacetal, that is the CHO group is not free. And similarly, when I say hemiketal form, in the cyclic structure of carbohydrates, the C double bond O combines with an OH group, is OH group, to form a hemiketal, that is it is the C double bond O is not free. Okay, so after a while we will see this in the form of structures. Okay, so those carbohydrates which contain aldehyde and ketone group which are not free, and they usually combine with an OH to form or to exist either in the form of a hemiacetal or in the form of a hemiketal, and also they reduce Tollens and Fehling solution. They are known as reducing carbohydrates or sugars. Okay, and all the monosaccharides, whether they are aldoses or ketoses, are reducing sugars. Very important. Okay, all monosaccharides, whether aldose or ketoses, are reducing sugars. Okay, by aldose I mean those monosaccharides which contain CHO group in the open chain form, for example D plus glucose. Okay, so aldoses are those monosaccharides which contain CHO in open chain form. Example, we have D plus glucose. Okay, for the structure of D plus glucose is C double bond OH, CHOH, COH, H, CHOH, CHOH, and CH2OH. So this is D plus glucose. And ketoses are, those monosaccharides which contain C double bond O in the open chain form. For example, D minus fructose. The structure of D minus fructose is CH2OH, C double bond O, COH, H, CHOH, CHOH, and CH2OH, right? Now, looking at their structures, there should be a doubt that should come to your mind. How come ketoses like D minus fructose, that is these guys, how are they reducing? Because toluenes and Fehling solution are weak oxidizing agent that we know from aldehydes, ketones, and carboxylic acid. So therefore, toluenes and Fehling solution should act only on aldoses, that is these guys, because they contain the CHO group, right? Then how are ketoses, how are these guys reducing the Fehling and toluenes solution, right? That's the question, that's the doubt, that how are ketoses like this guy reducing Fehling and toluenes solution. Okay, so the answer to this is, we have observed that when glucose is treated with a dilute solution of alkali, for example, we have, let's say, D plus glucose, this guy. Whenever we treat this guy with dilute alkali, that is, it can be NaOH or KOH, basically OH minus, we observe that it undergoes reversible isomerization. That is, this guy, upon the treatment of dilute alkali, undergoes reversible isomerization. Reversible isomerization to form equilibrium mixture of D-glucose, obviously, D-fructose, interesting, and D-mannose. Okay, so you can see you started with a solution of D-glucose, but in the presence of an alkali, it underwent reversible isomerization to give you a equilibrium mixture of D-glucose itself, D-fructose, and D-mannose. Okay, in terms of structure, I can show it to you in this manner: CHO, CHOH. This is the open chain structure. CHOH thrice, CH2OH. So this is your D plus glucose. So this guy, in the presence of OH minus, is in equilibrium with CHO, COH, H, CHOH thrice, CH2OH. So this guy is known as D plus mannose, and this is in equilibrium with CH2OH, C double bond O, CHOH thrice, and CH2OH, and this is your D minus fructose. The same equilibrium mixture is obtained even if we start with D plus mannose or D minus fructose. Okay, so let's say instead of D plus glucose, I start with D plus mannose, so I will get this equilibrium mixture itself in the presence of OH minus. Similarly, instead of let's say I start, instead of D plus glucose, I start with D minus fructose, so in the presence of dilute alkali, I will get this equilibrium mixture. Okay, so because of this isomerization, fructose in the presence of OH minus, so whenever we have fructose, that is D minus fructose in the presence of OH minus, so this OH minus is normally present in your toluenes and the Fehling solution. So fructose in the presence of OH minus forms an equilibrium mixture, so it will give us this equilibrium mixture. So can you see, fructose, because of the isomerization, gives us a small amount of glucose also. So therefore, because of this D plus glucose, it can reduce toluenes and Fehling solution because of this D plus glucose. Although it itself does not contain any CHO group, it contains a C double bond O group. Okay, so therefore, all the aldoses as well as all the ketoses, they are reducing sugars. Okay, aldoses simple because they contain CHO group. Ketoses, they in the presence of OH minus, they undergo reversible isomerization to give us a small amount of D plus glucose also. For example, in the case of D minus fructose. So therefore, statement A is correct. Okay. Now coming to statement B. So statement B talks about oligosaccharides. Okay, oligosaccharides are carbohydrates which on hydrolysis gives 2 to 10 molecules of monosaccharides. Okay, so oligosaccharides are carbohydrates which on hydrolysis give 2 to 10 molecules of monosaccharides. Okay, for example, sucrose. Sucrose is an example of oligosaccharide. Okay, so which upon hydrolysis, that is, with respect to reactions, C12H22O11, which is our sucrose, plus H2O in the presence of invertase enzyme, it will give us C6H12O6, which is glucose, plus C6H12O6, which is fructose. Okay, so therefore you can see the units obtained after hydrolysis, that is glucose and fructose, are not the same. Okay, one is a aldose, the other one is a ketose. So therefore statement B is false. Okay, now coming to statement C. Statement C talks about starch and cellulose, and it is true because starch and cellulose are examples of polysaccharides. Okay, so polysaccharides are formed when large number of, maybe hundreds to even thousands of monosaccharides molecules joined together with elimination of water molecules. Okay, so starch and cellulose, so they are examples of polysaccharides, so which are formed when large number of hundreds to thousands of monosaccharides join together with the elimination of water molecules. Okay, coming to statement D. Statement D is a true statement. Okay, the open chain structure or the form of D plus glucose is, so let's draw the open chain structure of D plus glucose. C double bond OH, CH, OH, CH, OH, CH, OH, CH, OH, and CH2OH. Let's give them numbers: 1, 2, 3, 4, 5, 6. So as I have mentioned earlier, that is in the cyclic structure. So this is the open chain structure of glucose. Okay. In the cyclic structure, the CHO, that is this group, is not free because the C5OH, that is this C5OH, combines with the C1 aldehyde group. So these two groups combine together. Okay, an aldehyde and an alcohol molecule combine together to result into a hemiacetal formation. Okay, so this is shown by these arrows. So this lone pair is given to this carbon. Oxygen takes away these um, pi electrons, and this H finally goes and combines with this O, becomes an OH. Okay, so as a result, you can see this carbon becomes chiral. That is, it has 4 different groups attached to it and has 2 possible arrangements of H and OH. That is, in one of them, H can be on left hand side, OH can be on right hand side. In the other form, OH can be on this side and H can be on the right hand side. Okay, so it results into alpha D plus glucose and beta D plus glucose. So all the three forms coexist at equilibrium. Okay, so using diagrams, I can show it to you like this. We have CHOH, CHOH, COHH, CHOH, CH, CH2OH, and this O. So this is, our alpha D plus glucose. This is one of the closed structure. This is in equilibrium with the open chain structure, that is this guy. So I will draw it again for your understanding. CH double bond O, CH OH, third carbon it's reverse, OH H, CH OH, CH OH, and CH2OH. So this is the open chain form of D plus glucose. Okay, and this guy is in equilibrium with beta D plus glucose. Okay, so in beta D plus glucose, just these groups are reversed. Okay, so we will have COH and H, and everything else will remain same. CHOH, COH, H, CHOH, C, H, and CH2. Okay, so this is our beta D plus glucose. Okay, so you can see these three forms, that is the open chain and the two cyclic structure, that is alpha D plus glucose and beta D plus glucose, are in equilibrium with each other. They coexist at equilibrium, and certain properties are explained by the open chain structure, certain properties are explained by the closed structure. Okay, so therefore statement D is also correct. It's a true statement. So in the question they are asking us which one of the following is incorrect. So A is true, sorry, A is true, B is false, C is true, D is also true. So therefore the correct answer is B. Statement B is false. Okay, thank you.